Hello, welcome to CSC7913, Advanced Math for Computer Scientists. This is Brady Chen. Today we're going to talk about Module 9, Introduction to Number Theory. Number theory has many applications. The well-known RSA crystal system is built upon number theory. So that's something we're going to talk about in this module. Now we're going to divide Module 9 into three parts, A, B, and C. In Module 9A, we're going to talk about the concept of divisibility and the division algorithm. Also, we're going to talk about the Euclidean algorithm, which is used to find the greatest common divisor. Now, in number theory, we're mostly dealing with the integers, the whole number. And some of the topics are so simple that they are even covered in the elementary school. So the first thing we're going to talk about is the divisibility. Let's first define what does it mean that the B divides A. Okay. So we say that a number which is non-zero number B divides A if we can write A as the multiplication of B and another integer M. Okay. So in here, all the numbers are involved are integers, A, B, and M. So B divides A if A equals M times B. So also, if we say B divides B, that means you can actually divide A by B, and there should be no remainder on the division. For example, so let's talk about two numbers. Okay, let's say B is 3 and A is 18, right? So then from the definition, we know that the B divides A. Why? Because we can write A, which is 18, equals 3 times or 6 times 3, right? And 3 is a B and 18 is A. So we can write A as the multiplication of 6 and 3. So that means B divides A. Or in another words, we can verify this by doing the division. We do the 18 divided by 3, right? A divided by B. Then we can say, okay, we can put a quotient 6. And we got the result 18, and 18 minus 18, which is 0. So 0 is the remainder. Okay, now in this case, remainder is 0. So that means 3 divides 18. Now in math, we use the notation B, and a vertical line means B divides A. Okay. Now, in case that we can write B divides A, we basically say B is the divisor of A. So in this case, in case B is 3, A is 18. So B 3 divides 18. So then 3 is a divisor. Okay. Now we can easily find many examples, right? So for example, the positive divisors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24 itself. Why? Because one divides 24. 2 divides 24, 3 divides 24. So all these numbers divides 24. So these are all the divisors of 24. Okay, so here are some more examples. 13 divides 182, minus 5 divides 30, 17 divides 289. So let's check this one. It's not trivial, right? So let's say 289, 17. So we can do the division. We can put the 1 here. 1 times 17, and then 28 minus 17. So it's 119. Let's say, yeah, we can put the 7. 7 times 17, so that's 119. Okay, that's 0. So we can do the division. 289 divided by 17, and we know the quotient is 17, and the remainder is 0. So 17 divides 289. That's pretty trivial. And 17 divides 0. Now, 0 is a very special number. So why 17 divides 0? We can actually check from the definition, right? If we say B divides A, then we can write A equals the M times B, right? So if we want to say 17 divides 0, now if we can write 0 as 17 times some number, then we say 17 divides 0, right? Now this is pretty simple. 0 can be written as 0 times 17. So 17 divides 0, right? For some 0 or some number. So 0 is a very special. Actually, so any number divides 0, right? So because any number can be written as 0 can be written as 0 times any number. So not just a 17. So 16 divides 0, 3 divides 0. So any number divides 0. So that's the divisibility. Pretty simple, very basic concept. So let's talk a little bit more about the divisibility. Now, some of the properties listed here are very trivial. Okay, let's take a look at each of these. Now, 1, if A divides 1, then you can say A could be either 1 or minus 1. Now, this looks very trivial, right? If any number, because 1 is the smallest positive integer above 0, so 0 is different. Now, if anything can divide 1, then that number is no longer an integer, right? So that means the only thing can divide 1 is the 1 itself, and or minus 1. Okay. Now, the second property, if A divides B and B divides A, then A and B are the same, or they have the same value but with a negative sign. Now, how can we actually show this is the case? Now, we can easily prove this by definition. Okay, let's take a look. So, what does it mean A divides B? Okay, so that means I can write B as the multiplication of a number M times A, right? If you forgot that, check the previous slides. So that's a definition for A divides B. Now, what does it mean that the B divides A? So that means I can write A as a multiplication of B and a number. In this case, I use n. Okay. So these are based on the definition. So now, if that's the case, then we can continue. We can combine these two equality. B equals m times A, and now we know A equals n times B, right? So I can replace A with n times B. So then we got m times n equals B. Now B equals m times n times B. Now, if B is non-zero, of course B has to be non-zero because otherwise B cannot be a divisor, right? And A cannot be a zero as well because otherwise, if we try to divide something by zero, that doesn't make any sense. So then we can cancel the B on both sides, right? B equals m times n times B. So we can cancel the B on both sides, replace with 1. So we got 1 equals m times n. So that means either n divides 1 or and it's actually n. M divides 1. So that means n is positive or minus 1 by the first property. And also m could be positive or minus 1. Okay. So what does that mean? So that means B equals, we'll replace n with positive or minus 1. So B equals plus or minus A. Or vice versa. A equals plus or minus B. So either way, doesn't make any difference. So we got this. So if A divides B, B divides A, then A and B are basically the same number. Or maybe the opposite number with the same absolute value. That's trivial. Any B which is non-zero divides 1 or divides 0. Okay. So that means B divides 0 for any non-zero number. Why? Because 0 can be written as a B times 0, right? So B divides 0. Now, the fourth property, if A divides B, B divides C, then A divides C. Now, to prove this again, we're going to use the definition of of this division. So let's prove this. A divides B implies that I can write B as A multiplied by some number, right? And B divides C, that means I can write C as B times n for some n. That's by the definition of the division. And then we can combine these two items. So C equals n times B, and then I replace B using this statement, right? So I can say n times m times A. Okay, now I can write C as a multiplication of A times a number. This number is n times m. Okay, m. What does that mean? By definition, that means A divides C, right? Because C can write as A times a number. So A divides C. Okay, now here's the example. 11 divides 66, 66 divides 198, then it's trivial, right? We can easily verify this. Now here is another property of divisibility and its proof, okay? So if B divides G, so B is a divisor of, right, of G, and also B divides H. If B divides G, B divides H. And then we know B divides M, some number M times G plus another number N times H. Now for arbitrary integers M and N. So this is always true. Okay. Now how can we prove this? Again, we use the definition of the divisibility. Now, if B divides G, then G can be written as B times some integer G1, right? And I use the integer G1. Now, B divides H, then H can be written as B divides some integer H1. Okay. Now, how can I prove that the B divides mg plus nh? Again, based on definition, if we can write mg plus nh as the multiplication of b and another number, right? So let's do this. So mg plus nh, mg plus nh. Now, if we can write this as a multiplication of b times some number, then we can say b divides mg plus nh. So then we replace g with this, right? Because g equals b times g1. So we replace g with b times g1. And replace h with b times h1. Okay. So now what? So we find out in these two terms, they have a common factor b, right? So we can take a b out using some of the basic number theory. What is this called? A distributive law, right? So I can take b out, and then the first item becomes m times g1. The second item becomes n times h1. So now I can write mg plus nh as a multiplication of b and another number. So we can claim b divides mg plus nh. Okay. Now here's an example. Now b is 7, so that's the one. And g is 14. 7 divides 14, right? And the h is 63, so 7 divides 63 as well, right? 63, 7, 9. Okay. So that means 7 divides 14, 7 divides 63. Now, we just want to make sure, 7, okay, I missed this extra vertical line. So that means we need to show 7 divides 3 times 14, 83, plus 2 times 63. Because 7 divides 14, 7 divides 63. So then we just, 14 multiply any number, in this case 3, and the 63 divides times any number, in this case it's 2, then 7 divides this one. Okay. So it's pretty simple. We can write this one as 7 times something. We can actually like take the 7 out as a factor. So 7 divides this number, right? Okay. Now let's talk a little bit more about division. So let's given any positive integer n is a positive integer, and any non-negative integer a. So a could be positive or 0. Now if we divide a by n, now keep that in mind. N may not be able to divide a. So that means a may not be able to write as n times any number. Okay? We may not be able to do this. So that means a is probably not a multiple of n. Okay? So in that case, if we divide a by n, we may get a quotient. And then we may get the remainder. Okay? Which is non-zero. Okay, let's talk about this a little bit more and by an example. Let's say n equals, so in this case, n equals 15, a equals 70. Okay, so that's the example. So we actually start from 0, and that number is 70, right? That's 70. So if we divide 70 by 15, divide a by a, which is 17, by n, 15. Then we can actually visually, using this diagram, say, okay, let's divide 70 by 15. So let's cut the 70 into a smaller piece of 15 each. So that's 15. Okay. That's another 15. So when we start from 0, then we end up at the 15, right? That's one section. And then let's cut another piece of 15. So if we start from 15, then we end with 30, right? And let's cut another piece of 15. So from 30, we ended at 45. Let's cut another length of 15. So from 40 to 60. Okay. Now, so we're now at the 60, right? Now, if we try to cut another piece of 15, then we find out that's not possible, because there's only, from 60 to 70, there's only 10 remains. So there's no way we can actually cut a small portion of 15 from 10, right? So that 10 is called remainder, right? And so let's see. So we can write 70 as the sum of all these 15 fragment, right? A fragment of 15. So how many of them? 1, 2, 3, 4. So we have 4 fragment of 15 each. So that's total of 60, right? Which is 60. Okay. And then we have 10 remains. So we have a total of 70, and we cut a smaller fragment of 15, and we have total 4 fragment plus a remainder which is smaller than 15. If it's greater than 15, we can cut another piece, right? But it's smaller than 15. That it's 10. So we can write the whole length A as 4 times 15. So there's a 4 fragments of 15 each. So 4 is the quotient, and 10 is the remainder. Okay. So we can write 70 as the 4 times 15 plus 10. Now this is generally true. So now we're talking about a piece which is A. So the size is A. Now we want to divide A by n. Okay, so then we cut into a fragment of length n. Cut another fragment of length n. Cut another fragment of length n. Right? So then we continue to cut until we got, 1, 2, 3, and the last piece is Q. Okay, 1, 2, 3, all the way to Q. And then now Qn is smaller than A, but the distance between Qn and A should be smaller than n. Otherwise, we can cut another fragment of n, right? Now this is the remainder. Okay, this is the remainder. So then we can write A as the sum of Q times n. N is the divisor. Q, 1, 2, 1, 2, 3, Q. That's the number of the fragments of length n. So that's the quotient. Okay. Plus the remainder, which is R. That's the remainder. So we know that the R is less than n and greater than or equal to 0. If R equals 0, that means n divides A, right? If R is 0, n divides A by definition of divisibility. Now, if R is non-zero, then A can write as Q times n plus R. That's a division algorithm. And now, many times we call Q the quotient, which is actually the value of A divided by n. Now, we use this square bracket to represent, sometimes we call the floor division. That means A divided by n, which is a whole number plus a fragment. And if we throw away the fragment, we keep the whole number. That's the quotient, Q. Now, I think we have enough knowledge to build our next algorithm. It's called a Euclidean algorithm. Okay, if you look at the picture here, that's the ancient Greek mathematician Euclid. Okay, he actually basically invented this algorithm. Okay, it's one of the basic techniques of number theory. Now, the Euclidean algorithm is used to determine the greatest common divisor of two positive integers. Okay, now, so suppose we have two numbers, okay, like two positive numbers, 132, 58, okay. Now, we can actually find the divisors for each of the number, so that find the list of numbers that they can divide 132. Now, this requires a lot of work. And then we can also find the divisor of 58. And now we know some of the divisors are common divisor. For example, 2 divides 132, right? Because 132 is an even number, so it can be divided by 2. And 58 can be divided by 2, so 2 divides 58. So in this case, 2 can divide both number. So 2 is the common divisor. Okay, and now we make be able to find more common divisors. Okay, now in order to find the greatest common divisor, that means it's a common divisor. It divides both numbers, but it's the greatest one, the largest one. Now, typically, you need to find all the divisors for 132, and we find all the divisors for 58, and then we just compare the list of divisors for both numbers, and we find the largest one. This requires a lot of work. Now, Euclidean algorithm allows us to quickly determine the greatest common divisor of two positive integers. Okay. Now, based on this, you can easily find whether two numbers are something called relatively prime. That's the other concept that we're going to talk about. Okay. Now, for now, let's actually skip that third statement. Okay. So, the greatest common divisor of two integers a and b is the largest integer that divides both a and b. Now we can actually take a look at a very simple example. Let's say 15 and 12. So we know that 1 can divide 15, 3 can divide 15, 5 can divide 15. What else? 15 itself can divide 15, right? 12, 1 can divide 12, 2 can divide 12, right? 3 can divide 12, and 4 can divide 12. 6 can divide 12, and 12 can divide 12. So now we know that 1 can divide every number, right? So 1 is always the common divisor. That's trivial. So we normally ignore the number 1. And also, every number can divide itself, right? Every number can divide itself. Now, in this case, we try to find first one, the common divisor. The second is the largest common divisor, the greatest common divisor. Okay. Now, what's the common divisor? 1 is common divisor. No question about this. 3 is a common divisor, right? 5 is the divisor of 15, but not 12. And 4, 6, 12, these are all the divisor of 12, but not 15. So looks like a 3 is the largest common divisor. Okay. So that's basically the way we can use to determine the largest common divisor. But that's not the easy way. Because if the numbers are big, then it's not easy to list all the divisors. So, so if for the greatest common divisor, we can use the notation GCD, greatest common divisor of A and B. Okay. Now, the GCD 0, 0, that's a very tricky one. And honestly, the GCD of 0 and 0 can be any number if we don't actually define this. So that's why in math, we have to actually set this, assume that the GCD of 0, 0 is 0, because 1 is also a common divisor of 0, 0, because any number is a divisor of 0. So that means, GCD of 0, 0 could be 1, could be 2, could be any number. So the greatest common divisor of 0 and 0 doesn't exist, right? Because 100 is the common divisor of 0, 0. 200 is common divisor of 0, 0. So which one is the largest one? There's no limit. So in math, in this case, to make our math theory simple, we simply define the greatest common divisor of 0, 0 is 0. It's not because that's the only one, because, if we don't define this, it's not determined. Any number could be the GCD of 0, 0. So we assume that the 0 is the one. Okay. So to define the greatest common divisor, we can also use another. You can say this is a definition, but it's also the property of the greatest common divisor. Okay. Now, a positive integer c is said to be the GCD of a and b if c is a divisor of a and b. Okay. So c is a divisor of a and b, but you may actually have many divisors, right? So then the second item says any divisor of a and b is a divisor of c. Okay. So now if these two conditions are true, then we are pretty sure that the c is the greatest common divisor. So let me say it again. So for a positive integer c is said to be the greatest common divisor of a and b if, number one, c is the divisor of a and b. Number two, any divisor of a and b is a divisor of c. Then c is the greatest common divisor. When we think about this, it looks like this should be the truth, right? And it is true. We can actually prove it. But at this moment, we just list this as another definition for the greatest common divisor. Okay. So we can use the equivalent definition for the greatest common divisor. Okay. So the greatest common divisor of a and b is defined as the maximum number of among all the k such that k divides a and k divides b. Okay, so k divides a and k divides b means k is a divisor of a and b. And now we just say, okay, among all the numbers k that divides both a and b, we choose the maximum number, and that's the greatest common divisor, right? So for example, in this example, we know that the list of k could be 1. 1 is a common divisor, right? 1 divides a, 15. 1 divides 12. And also, k could be 3, because 3 divides 15, 3 divides 12. And then we choose the maximum between these two numbers. So the maximum is 3, right? So that's another definition. Now, because we require that the greatest common divisor be a positive number, okay, so then if we talk about the greatest common divisor of a and b, and then if a is like let's say a is 8, b is 12. Now, then we know the GCD of a and b is, what's the greatest common divisor of a and b? It's actually 4. We know 4 divides 8, 4 divides 12. But you cannot find any bigger number that divides both a and b. Now, what about this? A is negative 8, b is 12. So then we say that, of course, negative 4 divides negative 8, negative 4 divides negative 12. But by the definition, the greatest common divisor has to be a positive number. So it's also 4, right? So the greatest common divisor of negative 8 and 12 is also 4, even though negative 4 divides both numbers, but by the definition, to make sure it's the greatest common divisor is unique, we always assume it's a positive number. So the greatest common divisor of -8 and 12 is also 4. So in general, we can say, greatest common divisor of A and B, the greatest common divisor of A and minus B, and the greatest common divisor of minus A and B, and the greatest common divisor of minus A and minus B are the same. Okay, they're the same. So in that case, so any time when we try to figure out what's the greatest common divisor of two numbers, whether they're positive number or negative number, we can always ignore the negative sign and keep the positive one. So that's why, in general, regardless the sign of A and B, A could be positive, B could be positive, or A could be negative, and B could be positive. So, it doesn't matter whether A and B are negative or positive. We can always think about the greatest common divisor of absolute value of A and an absolute value of B. We can always think about a positive number. So if someone say, what's the greatest common divisor of minus 181 and minus 131, then we can always convert the problem to find the greatest common divisor 181 and 131. We can actually find this one, and once we find the greatest common divisor of this problem, and then we say that's the same number for this, the same result for the top problem. So every time we can ignore the negative sign. Okay. Also, because all non-zero integer divides 0, we always have the greatest common divisor of A, and the 0 is the absolute value of A. Okay. If A is a positive number, it's A. If it's a negative number, then it's the absolute value of that number. Okay. Now we stated that the two integers. Remember the previous slides. I just actually skipped the last statement. We talked about the relative prime. Okay. So we stated that the two integers A and B are relatively prime if their only common positive integer factor is 1. Or in another word, so we actually say that the A and B are relative prime if the greatest common divisor of A and B is 1. So if I have two numbers and the greatest common divisor is 1, that means the only common divisor for these two numbers is 1. That means these two numbers are called relatively prime. Now, you should keep in mind that the concept of relatively prime is not the same as prime. Okay. Now, what is a prime? We're going to define this later. A prime number means that that number can be divided by either 1 and itself and nothing else. So prime number is the number which is not divisible. So no other number can divide that number. Okay, that's a prime number. Now relative prime means these two numbers has no common factors except for 1. As we mentioned, that the 1 can divide any number. So 1 is actually out of the question. So we normally treat 1 as a very special number. But if two numbers, the only common divisor is 1, then we are called these two numbers a relative prime. Okay. Okay. Now let's state what is the Euclidean algorithm. The Euclidean algorithm that is used to computer to calculate the greatest common divisor of two numbers. Okay. Now the Euclidean algorithm is based on the following theorem. You probably actually are confused with the notation. So then let me explain this. In order to find the greatest common divisor of A and B, now we assume that both A and B are positive, right? If it's negative, we just switch the sign to positive. And this won't actually change the result. So the greatest common divisor of two positive number A and B is the same as the greatest common divisor of the number B and A modular B. We never mentioned that before, A modular B. And in many cases, people use this notation. Okay, percentile. Now, what is A modular B? A modular B is the remainder when A is divided by B. Remember the remainder, right? So when we divide A by B, then we cut A into a chunk of fragment, each of length B. So we chunk B, 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 and each of is B, and then the remainder is a small piece which is smaller than B. If it's greater than B, we can still cut, right? Now, A modular B is the remainder when A is divided by B. Now, what does that mean? So the remainder should be A modular B, which is a remainder when A is divided by B. So the remainder must be smaller than B, right? Because A divides by B. Okay. And then remainder should be smaller than B. If it's bigger than B, we can divide cut another chunk of fragment B, right? So now, when I say when you calculate the greatest common divisor of A and B, you can actually do this. You calculate the greatest common divisor of B and A modular B. Modular B. So that means, if A and B are two numbers, and these B and A modular B are also two numbers, but they are smaller than A and B. We're going to use some examples later. And this is actually the algorithm. We can use this algorithm, okay? It's called a recursive algorithm, okay? Because when you actually define this Euclid of A and B, then we can actually eventually return the Euclid of B and A mod B, which is so this is called recursive algorithm. That means in order to solve the problem, we can actually eventually turn the problem into the same problem of smaller scale. Okay, so let's actually look at the example. Okay, here we're going to actually look at the example of finding the greatest common divisor of 710 and 310. Okay, now the Euclid algorithm is pretty simple. Okay, now the idea is, in order to find the GCD of 710 and 310, we just need to repeatedly use the algorithm we just discussed in the previous, right? So let's first look at the diagram. Let's understand how we can actually do this. So suppose that in general, we want to find the GCD of A and B. Okay. Now, first thing we need to do is we want to actually switch the value of A and B. We first assume both A and B are positive, because if it's negative, we can turn into a positive, right? And this doesn't actually change the result. So if A and B are both positive, and we also gonna actually switch the value of A and B if A is smaller than B. We just want to make sure A is always greater than B. And this also won't change the result, because the greatest common divisor of A and B is the same as the greatest common divisor of B and A, right? It doesn't matter we switch the position for A and B. But to make it consistent, we always gonna do the switch. So let's say we start from here. So we first check the value of A and B. If A is greater than B, okay, if A is greater than B, now we swap A and B, okay? Okay, I'm sorry. If A is greater than B, if yes, we don't do anything. So A is greater than B, we don't do anything. But A is greater than B, if the answer is no, it's actually B is greater than or equal to A, then we swap A and B. After we swap, then we move forward to the next step. Now, then we divide A by B. So now you know why we always want to swap A and B, to make sure A is bigger than B, right? Because we always going to divide A by B. So we have to make sure B is smaller than A. Okay? Otherwise, if we actually divide a smaller number by a bigger number, then we always get the same result, that the quotient is always 0, because there's no way we can divide a smaller number by a bigger number. But the remainder is always A in this case. So it doesn't make a sense. You don't actually gain anything, right? So we always make A bigger than B. So then we divide A by B. Okay? When we divide A by B, then we're supposed to have a remainder. Okay? So then, if the remainder is greater than 0, that means B cannot completely divides A. Okay, there's a remainder. So if the remainder is greater than 0, then what we're going to do is we replace A with B. Replace A with B. So in that case, so we replace A with B. Okay, replace B with R. Replace B. Replace A with B. Replace B with R. Okay. So okay. Now in algorithm, we just say we still do actually find the greatest common divisor of A and B, but in this case, in the second round, A is already not the original A, it's B now. B is not the original B, it's actually the remainder when A is divided by B. So this basically give you the clue that you still are going back to these step, but the value of A and B has been changed. Okay, now we actually keep doing this, keep this circle until R greater than 0 is no longer true. That means R is 0. So if R is 0, that means the remainder is 0, then we know that the GCD is the final value of V. Okay. So now when you check this, you will find out you find that the greatest common divisor for A and B, then we say, okay, I don't know what is the common divisor, but I know the greatest common divisor of A and B is the same as the greatest common divisor of B and R. Now in this case, A is bigger than B, right? B is always smaller than A. But now we replace A with B and replace B with R. So B is smaller than A and R is smaller than B. So that means we turn the original problem of the greatest common divisor of A and B into the same problem, of smaller numbers. So in this case, B is smaller than A, R is smaller than B, right? Now, if we still actually find out that R is greater than 0, and then we can continue. Okay, so we're gonna replace B by R and replace R by B modulo R. So that means divide B by R and with the remainder. So we actually gonna make it smaller and smaller. Okay, so eventually, once the number is too small, that until R is 0, then we finish. Let's check this. So we can actually turn the problem of finding the greatest common divisor of 710 and 310 into the problem of finding the greatest common divisor of 310 and 710 modulo 310. Now, what is 710 modulo 310? That's a remainder, right? When we divide 710 by 310, now let's do this. It's 2. Right? So now 710 divided by 310, we got a quotient 2 and remainder 90. So that's a remainder. So this is the same as GCD 310 and 90. So we turn the original problem into the same problem of smaller numbers. Of course, it should be easier to calculate the greatest common divisor of 310 and 90 than 710 and 310, right? Now, we can repeat this process, right? So now, the GCD of 310 and 90 can be calculated by changing it to a smaller, the same problem with smaller scale. Right? And replace 310 with 90, and replace 90 with 310 modulo 90. Okay, now what's the 310 modulo 90? And we're going to do another division. Okay, let's actually do the other division. Okay, what I'm going to do is I'm going to erase that one. Okay, I'm going to erase that one. Okay, so then we can do the division again. 310 divided by 90. We can say 327, right? 3 times 90 is 270. 0. And what's that? 4. Right? It's 11. 11 subtract 7 is 4. And because we borrow 1 from the 100 position, so it's 40. So now this is even smaller problem than the previous one. Okay, then we continue. And GCD of 40, 90 modulo 40. And what is 90 modulo 40? So we're going to do the division again. Let me actually put it over here. 90, 40, we'll put a 2. So 80, 10, right? So then we have a GCD of 40 and a 10. Now we are closer. So then it becomes GCD of 10 and a 40 modulo 10. Now what is 40 modulo 10? Because 40 divided by 10, we got a quotient 4 and remainder 0, right? let's say 40 divided by 10. It's a 40. So remainder is 0, right? So it's a GCD of 10 and a 0. So now we know that GCD of 10 and 0 is 10. Okay. So we find out the greatest common divisor of 710 and 310 is 10. Now, this over here, so we actually just write the same Euclidean algorithm using the math formula. So basically, the first actually equation means if we try to find the greatest common divisor between 710 and 310 is when we divide 710 by 310, we got a quotient of 2 and remainder 90. Okay, and then we turn the problem of finding the greatest common divisor of 710 and 310 to the same problem of finding the greatest common divisor of 310 and 90, right? And then we divide 310 by 90, we got a quotient 3 and the remainder 40. And then we turn these the GCD of 310 on the 90 into the GCD of 90 and 40. Replace 310 by 90, replace the 90 by 40. Okay, now we divide 90 by 40, we got a quotient 2 and remainder 10. And then we turn the problem of finding the GCD of 90 and 40 into the problem of finding the GCD of 40 and 10. So then we divide 40 by 10 and we got remainder 0, right? So that 10 is the greatest common divisor. That's the beauty of Euclidean algorithm. So we can try to find the GCD of two numbers, and then we convert the problem into finding the GCD of two smaller number by using the modular operation. Take a look at this example. This is very good, and we can actually work on 4 more examples if we have time. Now here, it's a much bigger problem. Now we know why we need a Euclidean algorithm. We try to find the greatest common divisor of these two numbers. That's a big number, right? So if I just put the common here, common here, common here, so it looks like that's 10 billion or 1 billion something, That's a big number. Yeah. I think that's the 316,258,000 and 250. That's a huge number. Now let's find the greatest common divisor of these two numbers. Now, if we don't use the Euclidean algorithm, think about this. To find the greatest common divisor of these two numbers, the first thing we need to do is find all the list of divisor for the first number and the list of divisor for the second number, and then we compare the list of the divisors of both of the number and find the common divisor and also the greatest common divisor, right? That's a lot of work. Now using the Euclidean algorithm, we can repeatedly use the formula that we can actually reduce the problem into the greatest common divisor problem of a smaller number. So let's say A is this number, the bigger number. B is a smaller number because B, this is bigger than B. The first number is bigger than B because it has one more digit. So the first thing we're going to do is we're going to actually divide A. We're going to divide A by B. So we got a quotient of 3 and remainder still a big number, right? But the remainder is smaller than B, right? So of course it's smaller than A because B is smaller than A. So R1 is smaller than B. Okay, so now the greatest common divisor of A and B, to find the greatest common divisor of A and B, we turn this problem into the problem of finding the greatest common divisor of B and R1, right? So it's now the GCD of A and B becomes GCD of B and R1. Now, let's repeat this. So we divide B by R1. So we got a quotient to 1, and then we got a remainder R2. And R2 is smaller than R1. Of course, it's smaller than R1, and R1 is smaller than B. So now we turn this GCD problem of B1 and R1 into the GCD problem, finding the GCD of R1. We replace B by R1, we replace R1 by I2, right? Still bigger problem. And then divide R1 by R2, and we got a quotient 2 and remainder. Now that's smaller. It's a 3,313,772. That's a smaller number. So then we're going to turn the problem of finding the GCD of R1 and R2 into the problem of finding the GCD of R2 and R3. So divide R2 by R3, we got a quotient 31. Wow, that's a good one. And then the remainder R4, which is smaller than this. Okay. Now, the same problem of GCD of R2 and R3 becomes the problem of GCD of R3 and R4. And then continue to divide R3 by R4. We got a quotient of 2 and a remainder. What's that? 137,984. It's even smaller. So it's still not 0, right? It's still greater than 0. So then we're going to continue to do this, and we replace the R3 with R4, and replace the R4 with R5. So now this problem, the original problem, after a couple of steps, the original problem turned into a problem of finding the GCD of R4 and R5, which is much smaller problem, right? And then when we divide R4 by I5, we got a Q6. That's 11. And the remainder R6. So then the problem becomes, the GCD of R5 and R6. So divide R5 by R6. Divide R5 by R6. We got a quotient of 1 and the remainder 67,914. And then convert the problem into a smaller problem. Replace R5 by I6, replace R6 by I7, and then divide I6 by R7. We got a quotient, and we got a remainder. Wow, R8, 2,156. Now the problem continues. We continue to do this. Replace R6 with R1, R7. Replace R7 with R8, and we divide R7 by R8. We got a quotient 31, and the remainder 1,077. Okay, now replace, still greater than 0, right? So replace R7 by I8. Now the problem becomes finding the GCD of R8 and R9, and divide R8 by I9. We got a quotient 2. We got remainder 0. Then we terminate, and we know this is the answer. So the greatest common divisor of these two numbers is 1078. Still a lot of work, but much easier than finding the divisors of both numbers and find the greatest one, right? That's still. And also, if we can write the computer program This is going to be very simple program. It's just a recursive program. Even the coding going to be very simple. Okay, that's the end of module 9A.